Hi everyone, this is the presentation for the adaptive ECG noise cancellation, and I'm Chen Yan. First, let me introduce the electrocardiogram, which is also called the ECG. An ECG is a testing method recording the electrical signals in the heart. Small electrical changes caused by depolarization of the heart muscle, followed by repolarization during each cardiac cycle, which is also known as heartbeat, can be detected by the electrodes. The abnormal ECG patterns often indicate different diseases, including cardiac rhythm disturbances, inadequate coronary artery blood flow, and electrolyte disturbances. However, most ECG systems require uh, comparable low noisy ECG signals. Uh, However, patient movement, bad electrode contact, and changes in electrode skin impedance can make the ECG signal be affected by noises, including white Gaussian noise, power line interference, baseline Wander noise, electrode movement, and Marshall artifacts. However, extracting the original ECG signal is always difficult with filters with fixed coefficients because because the noise added to the ECG signal often has a non-stationary property. Therefore, we often use adaptive filters in the noise cancellation of ECG signals. So, what is an adaptive filter? An adaptive filter has variable parameters which are tuned by an optimization algorithm, which is often used in denoising the ECG signals and can be shown as the updating coefficient equation, which is shown on the slide. Where at time n we add up the delta omega n to the last coefficient omega n at time n as a correction. The core of the adaptive filter is to determine how the correction equation is to be formed, which is also called the adaptive algorithm. A diagram explained in the adaptive filter is shown below, and according to different correction equation or the adaptive algorithm, we can have different adaptive filters. And we are going to use and introduce three adaptive filters in our project. The first is the RMS algorithm. The RMS algorithm is the least mean square algorithm, which is a particular application of the steepest descent adaptive filter. RMS filters have been used in a variety of applications, including system modeling, channel equalization, interference cancellation, adaptive antennas, and spectral line enhancement. The update rules of RMS are shown on the slide, where omega k is the estimated vector of the field coefficient at time k, and omega 0 is always initialized as vector 0. RMS algorithms are easy to implement, not too hard to compute, and is stable in a static environment, but the conversion speed is relatively slow. Another method is the NLMS algorithm, which is also called the normalized least mean square algorithm. It is an improved LMS by using the normalization, which means using a reparameterized step size. For input with large value, the LMS algorithm has a problem of gradient noise amplification, and it is necessary to set a very small step size to ensure convergence, which is also time-consuming. The NLMS algorithm solves the problem by introducing normalization of the input. And the last algorithm we are going to introduce is the RLS, which is also called the recursive least squares. It is an adaptive filter that minimizes weighted linear least square cost function related to the improved signal in a recursive way. This approach contrasts with other algorithms, such as LMS, which aims to reduce mean squared error. And the update rules of RLs is shown on the slide. Where theta 0 is often initialized as 0 and P0 is often initialized as the inverse of delta times the identity matrix. Well, delta is a very small positive constant, In most cases, RLS achieves the best effective noise cancellation performance, although it takes slightly longer to converge, but in the end, its error is always lower than the RMS. So to evaluate the outcome of these three filters, we are going to introduce three system metrics. The first is the the improvement in single to noise ratio, and which is also called the ISNR. The overall SNR distortion measures between an original single theta and an estimated single theta, which can be shown on the slide. Where is the difference between the theta and the estimated theta, and the ISNR is just the improvement in the single to noise ratio after filtering, and the MSE measures the average of the squares of the errors. Then let's come to the experimental setup. In this project, we use LMS, NLMS, and RLS algorithms to denoise four kinds of noises, which are white Gaussian noise, baseline van der Waals, electrode movement, and Marshall artifacts in the frequency domain. The ECG signal data is from the given ECG database.mat file, which includes the ECG signal and the noise we are going to investigate. The sampling frequency of the ECG signal is 500 Hz, and we have 5,000 samples in the digital form. We normalize the ECG signal to make the amplitude between the region to facilitate compression between signals. The normalized clean ECG we use for the experiment is showing on the slide. And here comes to the result of the white noise denoising. We use LMS and LMS and RLs to denoise the white noise. The first graph shows the amplitude of the ECG signal with white noise, and the other three graphs shows the results after filtering. And we can also see from the table on the right side that the RLS has the largest ISNR and the smallest MSE, while the NLMS is slightly better than the LMS. The second noise we are going to field is the baseline van der Waals. Still, the first graph shows the amplitude after we add the baseline van der Waals to the clean signal, and the other three graphs shows the result after we filled the signal. We can also find that RLS has the better performance, and then is the NLMS, and the LMS has the lowest performance. And this is the result for the Marshall artifacts denoising. Still, RLS has the best result, and this time NMS is only slightly better than the LMS. And the last one is the result for the electrode movement noise. RAS is still the best one, and then the NLMS is slightly better than the LMS. So here comes to the conclusion of the denoising effect. From the above results using the three-filter algorithm, it can be concluded that each algorithm can successfully remove four kinds of noise in the ECG signal. And RLS has the best performance in all four kinds of noises. And RLS is particularly useful for signals that may experience sudden changes in amplitude or frequency, such as muscle artifact noise, baseline van der Waals, and electro motion noise. This is because RLS is better at removing non-stationary noise. For LMS, since it on average goes in the direction of the stepwise descent, it moves around the true solution and is less optimal. And normalized LMS is more effective than the LMS because the NLMS has a time varying step size which is controlled by the norm. Therefore, we can see better performance in some certain noises like the baseline and vendor noise. And here is the comparison for the computational complexity. We can see that the RAS takes the longest time to compute, and then the LMS, and the last one is the best one is the NLMS. It concludes that among all three algorithms, the RLS takes the longest time to compute, which means the RLS is more complex than the other two algorithms. In fact, RLS takes more time to compute, especially when the field length is large. Normally, if we not care about the time for computation, the RAS is always the best choice. But if we do care about the computation time, we might use the NLMS as an alternative choice. So this is all for the presentation, and thank you for listening.